myself, so please hold your conversations. These two topics are really geometry things. So like you already kind of know what these are. Maybe the big change from geometry to algebra 2 is that I'm going to give you a formula that uses radians. You might already know a formula in degrees, but moving forward you're going to get this radians formula, so we won't be familiar with it. An arc length is basically a portion of the circumference. So it's not usually like the whole length around the circle, it's just a part of the circle. And so you know in a circle you have a radius, r, and then you have maybe some angle theta. And when you're asked about arc length, you want to know like what's the length of the arc that's intersected by that angle theta. So it's kind of like what we say in the definition of a radian, where the length of that arc would be equal to the radius. But you can have arcs of all different measures. So they could be longer than the radius, shorter than the radius. It's just whatever that measure or portion of the circumference is. For arc length, we use the letter S. Okay, so when you see S in the formula, that means arc length. And the formula for arc length is actually a very simple formula. It's S equals R times theta. But you can only use this simple formula if theta is in radians. It is possible for you to find what fraction of the circle that is in degrees. That's a different formula. And I'm really going to push you here in Algebra 2. Use the formula S equals R theta. That's a very simplistic formula. The only thing you have to know is that theta must be in radians first. So if I give you an angle in degrees, convert it. And that's going to give you the length of the arc or that portion of the circumference, okay, on the outer edge. For area of a sector, I'm going to draw another picture. And it would have like the same pieces, and who knows what the angle is. It can be a smaller angle, it could be a bigger angle. When I do area of a sector, I'm finding the space inside the circle. So it's like I'm finding the area of that pi piece, right? It's not the whole area of the circle, which would be pi r squared. It's a fraction of the area. The formula for area of a sector is 1/2 r squared theta. And if we have time at the end of the period, I'll show you like where those two formulas come from in relation to radians. But they're very simple. You just need theta to be in radians and then multiply it by 1/2 r squared and you've got the area of the sector. So these two things you kind of want to mark down. They're going to be like on your homework. You're going to make sure maybe that you write the formulas down, you show the work. Because on the quiz on Thursday, you'll be responsible for those two formulas. I will not provide them for you. So I would expect you to know S equals R theta, A equals 1/2 r squared theta. And you see it again in Algebra 3 or pre-calculus. To be real honest, these are two formulas. I don't always expect my pre-calculus students to remember on call, like when I ask them. But when I show them the formulas, they're always like, okay, yeah, I remember them. So it is one of those formulas maybe I don't always keep with me, but learn it, you'll see it again, and then it'll kind of stick eventually. Make sure that you have this note, theta must be in radians. That is for both formulas, arc length and area of a sector. That's a piece where even my pre-calc students, we're not paying attention to the detail. We leave it in degrees, you're going to get a wrong answer. Okay, there's a different formula in degrees. We're just going to focus on one formula in radians. So here's an example. Find the arc length and area of the sector with a radius of 5 centimeters and a central angle of 45 degrees. I mean, you're reading the directions and you have to do both, right? Arc length, S equals arc theta. Area of the sector, 1/2 r squared theta. And then I just gotta go digging for my information. Well, I know my radius is 5. And my angle is 45 degrees, but I got a little alarm going off, right? 45 degrees is no good for me. In my two formulas, I need theta to be in radians. So 45 degrees is one that eventually you'll know. Like, you won't have to actually do the conversion. It's one of what we call the special angles. But for right now, we can actually do the conversion. We want to get it out of degrees. So I'm going to put 180 in the denominator, get it into radians. Pi should be in the numerator of my conversion factor. And then just reduce 45 over 180, that is 1/4. 45 goes into 90 2 times, and 90 goes into 180 twice, so 45 is 1/4 of 180. So this angle is really pi over 4 radians. And like I said, at some point soon, you'll just know 45 degrees is pi 4. You won't have to do the conversion. That'd be nice. But if you don't know the angle, you'll do the conversion. Okay, so arc length, 5 times pi over 4. So you want to put that away from me, please? Yeah. And if you wanted to leave it exact, you could say like 5/4 pi or 5 pi over 4. But probably if you're talking about the arc length, is it an emergency? If you're talking about arc length, you probably prefer it as a decimal. So I'm going to do 5 pi over 4 in my calculator. I get 3.93. And then I think, did this say inches? Nope, centimeters. So my arc length is 3.93 centimeters. Okay, think about what that means in the picture, right? You don't always have to draw the picture, but it's kind of nice to like at least think about it. The radius is 5 centimeters. If I went straight up, that would be a 90-degree angle, right? So 45 is like halfway. So this is 45 degrees. And we just solved for the arc length. And we're saying that this arc length, this little arc, this little piece of the circumference is 3.93 centimeters. You know, if you think about the description of a radian that Morgan gave us at the beginning of class, is a good connection. 45 degrees is not 1 radian, is it? It's less than 1 radian. So this means, like, you know, if you were to create 1 radian in this picture, you would take this measurement of 5 centimeters and lay it on the circle, and it would be close to like a 60-degree angle. We said like 57 or 58 degrees. Okay? But because the angle is less than 1 radian, then the arc length is less than the radius. Right? That makes sense. If the angle was 120 degrees, I'm thinking that's almost 2 radians. So it should be pretty close to 10 centimeters. So you can kind of try to make that connection as well between the radian and the arc length. If I were doing area, I would do 1/2 times 5 squared times pi over 4. You know, that 5 squared is like 5 squared over 1. So if I leave it in exact form in the numerator, I'm going to have 25 pi. In the denominator, I'm going to have 8. And then I could type that into my calculator if you wanted to type in like 1/2 times 5 squared times pi over 4. That's fine. 25 pi divided by 8. That's going to be 9.82. What would my label be for area? Centimeters squared. Excellent. And so what that's talking about is, in this drawing, this space inside of this pie piece, that area is the 9.82 centimeters squared. Now the full area of the circle I would calculate at pi r squared, 25 pi. Think about 25 times 3.14, that's going to be over 75, probably close to 78. I've got 45 degrees of that. That's kind of like 1/8 of that. 78 divided by 8. Yeah, like 9.8 seems about right. So it's just a portion of the circle. So really today, if you know the formulas, and this is what it would be like on the quiz. If you know the formulas, just got to apply the right formula and make sure your angle is in radians and then plug and chug it down. It's not too bad. The last example that I want to show you, this is the one where we're going to pull back to that one on the homework that Van asked about. A carousel has a diameter of 25 feet, and it takes 15 seconds to make one rotation. If you ride the carousel for 2 minutes, through what angle do you rotate? So take a quick minute, talk to your group members. Can you determine the angle of rotation 2 minutes on this carousel? Share with your
groups. So you went around 8 times.
15 seconds.
8 times 360.
Oh, let's do it. So that's 8. That's 8 rotations.
Even 2 minutes.
It takes 15 seconds to make one rotation. Careful. 2 minutes. 8 rotations for 2 minutes.
2,000 divided by 2,280.
If it takes 15 seconds to make one rotation, what's your angle of rotation for 15 seconds? 360 degrees or 2 pi, right, in 15 seconds. But we're going to ride for 2 full minutes. So how many times are we going to go around? 8. 1 minute, if you're going 15 seconds around, is going to get you 4 rotations. So if you go for 2 minutes, you're going to have a total of 8 rotations, right? Now, you could get your answer by doing, I think Harvey gave me 360. You could do 8 times 360. I would have to pull out my calculator. Or I could do 8 times 2 pi, which is 16 pi. So there, I didn't need to pull out my calculator, right? I like radians. Okay, so my angle of rotation is 16 pi. Or whatever 8 times 360 is, a big angle. Okay, I think I have a follow-up question. You might have noticed in that question the diameter of the carousel was not any important information. It has nothing to do with my rotations, right? Okay. How many feet does a person on the outer edge of the carousel revolve? Well, now I'm starting to be interested in what my size of my carousel is, right? So I had some people, when I was walking around, I heard people reading it. The diameter is 25 feet, so what is important to me from that? The radius is 12.5. So I've got a radius, 12.5. And from the first question, what angle do I rotate? I have a theta in radians. If I'm on the outer edge of that carousel and I want to know how many feet I'm revolving, am I doing an area or an arc length on the outside? I'm doing an arc length. So in a problem like that, you would have to choose, like, what's the appropriate formula here? Do I want to do an arc length? Do I want to do an area of a sector? Well, I just have to do r times theta, and we said r was 12.5. Theta has to be in radians, so I would want to use that 16 pi. Type that into my calculator, 12.5 times 6 pi. And that's 235.62, is it feet that I was in? Yeah. So I would have rotated or moved 235.62 feet on the outside of the carousel. Now. Yes?
Say 6 pi, not 16 pi.
Oh, yeah, I put 6 pi, but it should be 16, right? I missed my 1 on my calculator. I'm sorry. It's bigger than that. 628. How about that? Should be 628.32 feet. Thank you, Harvey. Okay, now let me just say here, it should come up in a second, hopefully. Let me just say here that there's more than one way to do that problem. Of course, I kind of walked you through like arc length and area of a sector because that's the two formulas that I know. But if I had asked that question without like the angle of rotation, couldn't you have just figured the circumference of your carousel? 2 pi r. 2 pi times 12.5. 25 pi.